Hi, thank you very much for your interest to apply CC-GWAS to identify loci with different allele frequency among cases of different disorders. My name is Wouter Pirot, and the next 15 minutes or so I'll show you how to run the CC-GWAS software, as we also conduct this analysis in the cross-disorder working group of the PGC for the next wave of analysis. Elkes Price and I developed the software, and if you're interested in any further reading, please see our paper in Nature Genetics 2021 or visit my GitHub page. And if you have any questions or suggestions, please do not hesitate to contact me. I'm most welcome to explain further or to receive any suggestions you may have. So just at the end first, here I'll show a couple of slides to give a big picture overview of the method, and then I'll get on my hands on some real data to show you how the analysis are done with the R package software. So CC-GWAS is intended to compare cases of two different disorders, and when you like to extend, for example, to compare 10 disorders, you just need to repeat the CC-GWAS analysis accordingly to compare two disorders at a time. So CC-GWAS compares the cases of two disorders based on the respective case control GWAS results, and the case control GWAS results are of course widely publicly available most of the time. And CC-GWAS works with taking a weighted difference of these case control GWAS results. And CC-GWAS combines two components which have a distinct function. So the first component is what we refer to as the CC-GWAS OLS component, and this component optimizes the power and controls for type 1 error at null-null SNPs. And with null-null SNPs, we refer to SNPs that have no impact on either disorder, so there is no case-case difference. And if you're interested in any more details about the CC-GWAS OLS component, I refer to our paper. And then there is a second component, which we refer to as the CC-GWAS exact component, and the CC-GWAS exact component controls the type 1 error at stress test SNPs. And stress test SNPs are a very specific set of SNPs that impact both disorders, but have no case-case difference, so that the impact on both disorders is exactly the same, so there's no case-case difference. And this set of stress test SNPs is a very tricky set of SNPs because they can get type 1 error quickly. That's why we have this additional set of weights to control for type 1 error at stress test SNPs. And so CC-GWAS says that a SNP is significantly associated with case-case status when the p-value of the OLS component is smaller than 5 times 10 to the minus 8, and when the p-value of the exact component is smaller than 10 to the minus 4. And CC-GWAS has an additional filter to protect against false positives, and that is a very specific set of false positives that may result from differential tagging of a causal stress test SNP. So again, the stress test SNP is a SNP that impacts both disorders, but has no difference in allele frequency between the cases. And here in the right column, you can see the causal stress test SNP. So it has an impact on disorder A, it has an impact on disorder B, but there is no case-case difference, so there's no case-case effect. But now suppose that you have a tagging SNP, which tags in population A, in which you study disorder A with an R of 0.6, and disorder B, it tags a SNP with an R of 0.3. Then when you look at the difference of the disorder A and disorder B effects, you do find a case-case difference. So this is a very specific set of SNPs for which you can find false positive, and to protect against this SNP, CC-GWAS has an additional built-in step to filter SNPs that show evidence of differential tagging. Once again, when you're interested in any more details of this step, I refer to our paper and its supplements. So now we get to how to run CC-GWAS. So I first suggest to visit the GitHub page, CC-GWAS GitHub. And at this GitHub page, I would download all the results, and in particular, I already downloaded the files. In the test folder, there are the two dummy input files for the case control input GWAS results. So I'll return to the previous page. And here you can see an explanation of how to run. So running CC-GWAS, how to get started. There's a detailed description of all the input parameters where you can that you can look up for reference. And there's a description of the output files. And there is this example which I'll go through with you. So let's first get to running CC-GWAS. So first here I have a terminal opened, and I can show you I'm in a folder where I have already downloaded these two files. So the test case control GWAS for BIP 10 SNPs and the test case control GWAS for schizophrenia 10 SNPs. So we'll look at the example of comparing bipolar to schizophrenia. So back to the GitHub page. So now, and first we open R, and I'm working on my MacBook, but I note this is exactly the same as working on a Linux-based server, and it also works on Windows. Here, and you first need to load a couple of R libraries and install the CC-GWAS package. So I'll just copy paste it from here, paste it here, and wait for R to run it. And now CC-GWAS is loaded, and you can see that CC-GWAS is now a function in R. So you can see that CC-GWAS is now loaded into R. Okay, and I've already loaded these two files, so now I go to this example. Here at the top bottom of the GitHub page, I've loaded this CC-GWAS example, and you can see if it all works. And I'll copy paste it. And you can see that all is loaded. But before looking to the results, I'll first get to you to see the input parameters. So probably best do it on this GitHub page. So here you can CC-GWAS. First you set the name of the output file, and then you set the name of the first disorder. You set the name of the second disorder, which is bipolar disorder. You say where are the sum stats file of the first disorder and the sum stats file of the second disorder. Case control of the case control sum stats results. And I note the 6 columns of these results are very specific, so they need to be exactly as I've described it here. So let me show it at the GitHub page. So here it says, so the columns should be the SNP name, the chromosome number, the base pair position, the effective allele, the non-effective allele, the allele frequency of the effective allele, the odds ratio, for the risk of the disorder for the effect per effective allele, the standard error of the log odds of the log of the odds ratio, the p-value for this SNP, and n effective. And when you don't have n effective, you can impute it as I also describe here on the GitHub page. So 4 divided by 1 over n case plus 1 over n control. And I note that the results for the case control disorder A and disorder B will be merged on the SNP names. So before you run CC-GWAS, make sure that the SNP names between those two sets are well aligned. Okay. Now I'll return to the example that we just ran. So that's where we left off. I just showed you what the columns should look like of these two gzip files. And then there are more input parameters. So KA1A0 means it's the population prevalence of disorder A. So for schizophrenia, that's approximately 0.4%. And then because, of course, it's very hard to know exactly the population prevalence of a disorder, you can also put boundaries to it. And so for schizophrenia, we set it at 1% and the low at the 0.4%. And it's important to add these ranges because this also, again, protects against type 1 error at stress test SNPs. And then for disorder B, you set the exact same free values, so the population prevalence of disorder B and the high estimate and the low estimate. And then you specify results that typically come from LD score regression, but of course you can use different methods for it. That's the liability scale heritability for disorder B, the liability scale heritability for disorder B, and how to get to these estimates. I refer to the software package that provide these estimates. Then you want to know the genetic correlation between disorder A and disorder B, and also the intercept that you get from bivariate LD score regression. And this is very important to set this value because it helps you to increase the power of CC-GWAS. And you also set an estimate of the approximated number of causal SNPs. And so this M value, you need to specify it. And I also show here at the input files. Here, I give some explanation about it, and also some papers where you can see if this M is already estimated, or how you can estimate it, or if you want to make an approximation how to do it. So details on setting M is here on the GitHub page under the input parameters. So we were left here with specifying the number of SNPs. And then at last you need to give the number of cases for disorder A, the number of cases for disorder B, the number of controls for disorder A, and the number of controls for disorder B. And then you also need to specify the overlap of controls. And once again, when you set this overlap of controls, it really helps you to increase the power of CC-GWAS. And so it has kind of the same function as the intercept. So these are two ways to increase the power of CC-GWAS, and also to double check that you don't risk any type 1 error result. So when you know these values, it's important to set it to increase the power of CC-GWAS. So I hope this clarifies the input parameters of CC-GWAS. And now I'll return to the analysis that we just did by running this command line. So we just ran it, and you can see that the R function gives kind of an output file, which is also saved in the log file. So it says, well, when the analysis was started, and that you run CC-GWAS and not CC-GWAS plus. And for CC-GWAS plus, I refer to the GitHub page, and this is when you also have a direct case-case comparison available. And then it shows some summary about the data that were read from the gzip file, and it does some very rough QC on the odds ratios, and then how it merges the data, and so this kind of just the log file that's plotted, and you also get provided an FST plot for this. And let me see if I can quickly. Yeah. So this is what the FST plot looks like. It's an output of CC-GWAS, and here you can see the FST. Again, for the details I refer to our paper, but it gives intuition of the genetic distance between cases and controls. So here you can see the controls for bipolar disorder, the cases for bipolar disorder, the controls for schizophrenia, and the cases for schizophrenia. And I don't know what just happened. And these numbers gives the relative difference between them. So you can see that even though schizophrenia and bipolar disorder have a very large genetic correlation of 0.7, the genetic distance is still considerable, with a relative value of 0.49 compared to 0.66 or 0.6 for the case control difference. Okay. And then when we look at the output files, I always like this system where from R you can also use the command line in the terminal. Here you can see that by running CC-GWAS, these are the input summary statistics for these 10 SNPs. This is the output file. This is the FST plot that I just showed. This is the log file, which is also printed here on screen, so I'm not going to open it, but it's good for later reference if you're interested. And I note this log file also gives you the OLS and the exact weights that I just discussed. So here in the log file you can see, so for this example, the OLS weights were 0.54 for schizophrenia, minus 0.3 for bipolar, and the exact weights are also listed in the log file. It may be good to report this in the description of your CC-GWAS analysis. And here there's also the results that are displayed here. So now let's have a look at these results. I'll just copy paste this also from the GitHub page. And for now I'll remove the all and I'll explain to you later what all means. So I need to give it the correct name. Test out. And then let's have a look at D. So once again, I only have 10 SNPs now. Normally, of course, these are maybe 10 million SNPs or something. And here you can see the columns. So there's the SNP name, the chromosome number, the base pair position, the effective allele, the non-effective allele, and then you have 3 columns, OLS beta, OLS standard error, and OLS p-value. And these represent the effects from the OLS component of CC-GWAS. And then there are 3 more columns, exact beta, exact standard error, and exact p-value. And these three columns give the CC-GWAS results of the exact component. And now, as we said, and here there's also a column which labels CC-GWAS significant. So when CC-GWAS is significant, this column is labeled as 1. Right? So, and you can see for this specific SNP in the 9th row, so when we look here, you can see that the OLS p-value is 9 times 10 to the minus 12, so it's smaller than 5 times 10 to the minus 8. And you can see that the exact p-value is 4.7 times 10 to the minus 11, so it's smaller than 10 to the minus 4. So this SNP is CC-GWAS significant. So if you're interested, I think it's good to note that you can also have a more detailed output file. And to do this, you need to add to this R script. So you need to add here an additional input parameter, which was named, if I remember correctly. Yeah. So then you add save all is true. Here, save all is true. And then when we look again at the files that are now in the folder, here you can see that an additional output file popped up. And when we have a look at this file, so I open this file, changing the file name a little bit, add the all here. So, and now this file takes much more space. Of course, for 10 SNPs, it's not really a problem, but when you have many SNPs, it can be tedious. So, and there are many columns here. So the first columns of D represent again the columns that I just discussed. So the first columns are the SNP, chromosome, base pair position, effective allele, non-effective allele, and then you have the case control effects, and these are scaled to the standardized observed scale based on a 50-50 case control ascertainment. Again, when you're interested in any details, please see our paper and its supplements. And then you have the case control results for disorder B. Then you have the OLS results, as we just discussed, and you have the exact results. But then there are additional columns. So there is the potential tagging for the stress test SNP, potential differential tagging of the stress test SNP, and it's not necessary to understand all the details. If you're interested, please have a look at the at our paper or its supplements. But just know that behind the scenes we test for it, and it's being excluded from the previous output file that I showed. And then here we also have this exact approach, which again, so the exact component of CC-GWAS protects against type 1 error of stress test SNPs, and this is also based so that you don't know exactly the population prevalence of both disorders. So here you can see the exact results when you take the low values of both population prevalence disorders, low-high, high-low, and the high-high population prevalence bound. And here's the CC-GWAS significant folder. So as you can see, This output file all. If you're interested to look into more details of your results, you can have a look at it. And if you have any questions, please don't hesitate to contact me and ask me for the details. But in general, I advise not to look at these results because also in the trimmed results, which are the default output, and now I'm going to load it again. We already removed the snips that may have a problem with differential tagging or some other issues, right? So if you use this file, you're safe in that aspect. And then finally, and I see I extended the 15 minutes, but I hope you don't mind. So now we showed how to run CC-GWAS in practice, and for follow-up analysis, as I just said, use CC-GWAS results based on the save all is false results. And I know this is a default, so when you don't set save all, this is what's being done, and it's a trimmed set of results. And then we advise to use the CC-GWAS OLS components. So these are the columns that are labeled OLS beta, OLS standard error, and OLS p-value for clumping and, for example, polygenic risk score analysis. So to look at which loci have the different allele frequency. And when you're interested in genetic correlation analysis or any other sort of LD score regression-based analysis or methods that are alike, we advise to use the CC-GWAS exact components, so the exact beta, exact standard error, and the exact p-value. So that brings me to the end of this tutorial. Once again, please don't hesitate to contact me if you have any questions, and I hope this tutorial was helpful.